Thanks, Hatanas, for the introduction. Okay, my name is Reza Ghabcheloo. I'm today talking about perception sensor for autonomous mobile machines. And as Hatanas mentioned, the sensors and applications, algorithm, etc. we are developing here, they are not specifically for autonomous machines, so they can be especially used in assistive and operator assistant operator assistant systems. If you are from university, we are in the few faculties, and our faculty where I'm working on engineering and natural sciences, and we are in automation technology and mechanical engineering. First of all, I don't know what was in the morning. Sorry, I missed it. But I thought it would be good to see the application area. What kind of, when we say working machines or heavy equipment or non-road mobile machinery, what we are talking about. So we are talking about machines that are working in the off-highway. They are especially harsh conditions. So that means the certain type of sensor like RGB cameras are dark and dusty and fog environment. They have challenges. There are many variants compared to, let's say, drone industry or automotive industry. They are very specific and the numbers are high. So when you do something for one machine, you can basically extend it to millions of them. Here you have typically, let's say you have the Ponce machine and this cut to lens. They are produced 3,000-5,000 per year. So it means that when you do something for one machine or one application, you should be able to, they should be transferable, they should be extendable and etc. So they are also mobile manipulator, meaning that they work, they move and also work. So it's not just about moving. And they are, because they apply a lot of forces, they are typically hydraulic driven. Nowadays, there are a lot of activities in electrification of these machines. I will go very briefly on my research group, and then I will start in different categories of application where we use perception sensor. I will give an example. I'll try to be informal and relaxed, more video showing than really go into technical stuff. We can arrange different meetings for technical. My group, Autonomous Mobile Machines, we do a lot of stuff. As I showed, there's a big machine, so we work on the power transmission when you convert the prime mover, typically diesel engine, and nowadays electrical motors to actual work. So how to optimize those. We work on the controlling from sensor. Today we will hear these three topics in more details. And also we have been doing a lot on robot learning, trajectory optimization, motion control, etc. Couple of words about things we have. We have a robotics major where students do their studies continue the master's degree in robotics. There we have also 2017-18 we started this what we call the RoboLab, where we have relatively safe environment with the smaller robots, and the students have access to those robots, both manipulator type of thing, what we call these manipulators, and also mobile robots. And this is one of the actually students' project in one of the courses. They made this, and I give an example. Also, we have a sensor setup for a student to learn how to work with this kind of sensors. For a bigger application where my research goes, we have actually a test environment, 4,000 square meter behind the campus, not far from here, fenced area. And with some cold cabin, etc., and then the control station. We have actually recently also 5G access link there with very many machines that they work. We use them for pallet handling, earth moving, different kind of research, manipulation, and we are going to get soon a fully electric wheel loader also. We are working with many companies, and including you can see the names there in this, and also as autonomous advertised. I'm also leading a Marie Curie ITN program where there are 8 doctoral students doing their PhD partly at the university and partly at the companies. It has been working very well, and then some of these results I'm showing today are the work of those students. I categorized my my talk. Now I'm not following the time. When did we start? Well, we'll see. In several categories: vision-based servoing, vision-based obstacle avoidance, SLAM, motion-based calibration, and I had plans to talk about also some of the work we do on radars. I'll skip that one for today. Very good, thank you. That helps. Okay, first of all, when we talk about servoing, basically when you have a control system, like doesn't matter what it is, but it's like a robot that moves, either manipulator or a mobile robot. There are certain objectives. One of them is reaching to a goal. That's what we typically call servoing. So you want to pick an object. It could be a pallet, a container, or it can be at home to reach to get some object. So that's what we call servoing. So it's reaching to a goal pose, or it's actually following a trajectory, meaning that it could be just painting the wall. So it's not reaching a point, but it's about following. So it's about controlling. So this we started, I thought that's good to start with some historical stuff. Back in 2010, here you see a camera here. We actually did pallet picking with a camera in the loop. So we had everything in the software, simulation environment, and the system hardware, and actual camera in the loop. So we projected the thing on the wall and did visual servoing. And then we continued that in where RF did his PhD in 2013 to 18. We actually continued those lines of work and implemented those on real machine. This is actually our test area when I said that we have the fence area. So you can see here that you have a camera that basically should be able to detect what is in the environment you are trying to reach, in this case the pallet, and then try to control all your actuators, in this case booms and forks and the steering gas, etc., to reach the goal. We have quite many papers on this topic. Then, like 2019-20, we got a funding from Business Finland, something called Research to Business. Basically, the idea is that if you are mature in certain research area, you are planning to commercialize those, or you have a patent, etc., at university, so you get some funding, seed funding from Business Finland. So we have been doing a lot there. We haven't started any company spin-off yet, but we found we had a lot of interaction with the companies, even more than we had before. So for us was about packetizing some of the things we have been doing, especially about object detection, both using 3D sensor like LiDARs, depth sensor, etc., RGB cameras, using a simulation environment to train networks, or more classical, traditional way to do pallets, detection, tracking, etc. Okay. Then something different. That was the story of pallet picking. Then we started working with Yoni Cameron and especially Natalia. I don't know if Natalia is here today. And Venyan on earth moving. So the objective is that, okay, now you have a material in front of your wheel loader, and you want to make this robot to go and pick the material to fill the bucket. Let's see if I can open this. Okay, you need to skip the advertisement. So the point is that you have the material in front, you have a wheel loader, and the idea is that, okay, how you program your robot to actually do this. So what we did, it's about learning from demonstration. Basically, it's very difficult to model the whole interaction between the soil and the robot. So what we did was that actual driver, like an operator, in this case, for us, it was Nikolai sitting up there, not skilled, but more skillful than other postdoc students and doctoral students. So we basically demonstrated 50 times in this case, and then you have recorded data from the pressure sensors, angles, cameras, etc., and you generate a program or controller that basically controls the steering in the gas and the boom, etc., and does this autonomously. We have done a lot of work on that, several different papers and articles on that, and this is some of the things comparing different methods and showing that some of them are prone to fail. At the moment, I'm also working with some of the companies that are the, let's say, biggest producers of wheel loaders. You can see they are. We have fun. We have fun in the lab. So we haven't broken any machine. We have small crashes, yes, but hopefully nobody so far. In 14 years I have been working in this, we haven't had a serious accident. Okay, so here, as you can see, there are cameras that the vision input is fed to this, and this basically does feature extraction or model reduction, whatever you want to call it, and then those, including the other sensor like kinematic sensors, angles, etc., and speeds go into the controllers, and then those move gas bucket and boom to do this. Okay, so that was about the servoing side. So basically you have an object, you want to reach there. Now, other thing is that, okay, it's not only reaching somewhere, right? You want also sometimes to avoid them. So this is something called, what we call the vision-based obstacle avoidance. And special safety is a very recent result of, why is not working? I'll skip this part. Maybe I can start from here. Basically, there are different ways of doing it. More classical way is that you have a control system like sensors, LiDAR, etc. You decide, okay, this is drivable because this is a road, it's kind of flat, etc. And then this is not drivable, it's obstacle, it's a car, etc. And then you design controller like plan around the paths. And one of the things is the safety, meaning that although sometimes the planning algorithm may fail, but you want to make sure still you don't hit anywhere. So so the thing we did here was that so also most of the traditional methods, they assume everything is like circular or cylindrical, etc., very specific geometrical shapes of obstacles. So what we did basically in this recent work was that we basically used I will stop it here. So we use segmentation. So this means that your object not necessarily anymore circular. It can be a shape of a car, bicycle, etc. But as long as you have a segmentation, meaning that you, for each pixel in your image, you define this is something that is drivable, or is a car, or is something that you can actually annotate it. This is an obstacle, you need to avoid it. And then we basically trained to learn something like this, which is basically an image-to-image translation. You generate some sort of a field, and that field again goes to an optimization algorithm that does planning, does avoiding. So this is basically trained on a Carla simulator, if you are familiar with. And our method is because it's not fully end-to-end, it allows us to actually extend the result using several different cameras. So actually in this case, although we trained on one camera, but in actual implementation we have 3 cameras. Output of those enter the optimization, and then we use it for control. Just one advertisement, the person doing this, I have also a project called AI Hub Tampere, where we give different kind of services. One of them is workshops. So we have every 2-3 months workshop on a certain topic. In February, we are going to have a workshop on simulators. So we use a lot of different simulators, including car lawyer sim, ISAC, Gazebo, for different applications. Of course, we have also more high fidelity simulator that use more mechanics, like a sim mechanics, sim hydraulics. But in this case, we are really focusing on a simulator that are more used for learning for our application. So we'll have a workshop on there, 3-4 hours workshop that will show more details of our application and how to use simulators in robotics, basically. So we had this controlling, servoing, we had the obstacle avoidance, and then there are other things also we do with vision and perception. One is SLAM. You might be also, most of you familiar. Basically, what you want to do is that you want to localize the robot when you want to basically tell the robot to move to a certain place, and so that certain place need to be defined in certain coordinate system. And you need to know where the robot actually is in that coordinate system. And that coordinate system either is attached to a GNSS, your satellite system, or some local map, which in this case, we use what we call a SLAM. So you localize yourself with respect to the map you have. One recent paper we had was on comparing, because SLAM has matured a lot. There are still a lot of things to do there. And there was a lot of question of existing methods and comparing them. So we took 8 different algorithms of both LiDAR SLAM, so you map and localize yourself using a LiDAR, and also visual cameras, RGB cameras, and we compared them, including, let's say, SVO SLAM and or SLAM 3, etc., or HDL SLAM in this case. And as you can see here, our machine, one of the sensor setup we have there, including stereo sensors, LiDARs, different kind of LiDAR sensor. Beeper is a dome-shaped LiDAR, so it's not a rotating LiDAR. It's a rotating LiDAR, but it's not a 360 LiDAR. It's a dome shape, so it's for shorter range but higher field of view, obstacle avoidance type of application. And then we also have IMUs there. So what we did there was that the objective was to compare them in terms of accuracy, location of sensors. So we attach the sensors in the boom and move it up and down, see if the location of the sensor affects on the accuracy of these SLAM algorithms. And also speed of the machine, because these are basically rotating sensors, or depends on the vibration and speed that has an effect on those. Dynamic environment, if there are many people walking around, the machines coming and going, does it have an effect on those? We also tested many and also the CPU load. Some of them are lightweight, some of them are quite heavy, at least in certain time. That's our lab. It's old. It's actually a bit old because in this picture it doesn't have the fences and our test, some of the equipment we have in the test area. So here we drove this machine actually in this area, going around this is called the mobile lab, mobile hydraulics lab, and we store our machinery. You can see it here. This is Korka Kolumkatu. And as you can see here, you can also, these fences are now visible. In the original picture here is not visible, but here in the LiDAR map you see this. We have also mapped our campus, at least our Konettalo, where the machine building, where the mechanical engineering is located. Now, SLAM was more about pose estimation or localization of your robot. Depending on type of SLAM, it may provide also maps that are useful for obstacle avoidance. Basically, also tells you where the obstacles are. Some of them are not useful. They are basically sparse methods. Is that you have left some time for questions, or should I soon close it? I have one more slide. I will quickly go through it. So now you have a Compared to typical, let's say, application in this machine, they are very big. We use all different kind of modalities from the lidars, or different kind of lidars all over the machine, cameras, radars, sonars, and you want to integrate those all in the same model, right? To have an understanding of the environment. So you need to know where this sensor is with respect to the others. These are coordinate system of the sensors that are installed in this machine. Well, this is called extrinsic calibration. There are many methods. We have also experimented with something what we call the motion-based sensor-to-sensor calibration. And also you need to know the sensor with respect to the body, because if you want to move this manipulator or the body in certain location, and the sensor needs to know what is their relationship. So you can actually use this something called the motion-based method. The good thing about that compared to traditional is that in traditional you need to have both sensors seeing the same field. In the motion-based, they don't need to have necessarily the same field of view. So you basically write the optimization algorithm that does this. We have compared several different methods that exist in the literature. We propose a new method as well. The result you see here, basically what we did was that if you are familiar with the Kitty data, so here you basically drove the machine driving, you collect data. It doesn't necessarily need any infrastructure for calibration. So you have lidars and cameras, and based on these methods, you can actually tell where the camera is with respect to the lidar. So that is basically a summary of my work. I can stop here. It's a reminder of what I have been talking. You can ask questions. Thank you.
Thank you, Reza. Please, your questions. Yep.
Hello.
Hi.
So how does the machine figure out what is it okay to collide with, since it picks up gravel or ground, whatever? How does it figure out that it's okay to collide with this and that it goes to the same spot to get the gravel?
Yeah, that's a good question. Of course, there is a conflict, meaning that sometimes you want an object to pick, and sometimes you actually need to collide with it. It's okay to collide with something, but it's not okay to collide with something else, and they might look the same. Yeah, well, as I said, if it's we don't have a general intelligence, meaning that robots cannot really solve. They are not really autonomous, so they are programmed. So it's really the objective is you define. Now what you see in front is actually something you are allowed to collide, and there's maybe it's you can collide with your boom and bucket, but you're not allowed to collide with the back of their machine. So they are mostly programmed at the moment. There are a lot of work on what we call the long-term autonomy, meaning that basically you teach to the robot to be able to figure out what to do and what not to do. A lot of learning is there, and a lot of programming. Our students know to program, and they are good in maths.
All right. Further question? Yep.
Hi.
Yes. Hello.
Do you already have an autonomous program that tells you when the shuffle of the robot is actually full? Like, when does the robot? How does the robot know that he collected enough gravel?
The operation is so fast that is basically it's not about deciding when it's full, it's enough. Basically, it's kind of a you try to load as much as possible. That's typically the case, and at that point, basically the machine it cannot really move further. So the way is that it kind of goes forward, goes forward and lifts and goes forward as you kind of explain it. But of course, when you write a controller, then you don't. The traditional way we typically program it, what we call the rule base. Nowadays, but we don't do it. We basically train it using demonstration, and those are programmed without explicitly saying what to do, what not to do. So Our experiments show that if you have a very smooth gravel that's always the same type of thing, they are not very robust. But if you have a complex gravel and train it on a complex gravel, then it kind of extends better, more robust to different materials. And that means that it knows how to go forward and lift.
Okay.
It's not specifically measuring the weight, but of course, eventually, when we lift it, for data collection, we collect how much it been, how full it has been. Yes.
Okay. If it's okay, I would have another question. At the end, you talked about the calibrating of the sensors. I was wondering, at one picture you had the sensors actually on the shuffle of the car. I was wondering if it's then a dynamic problem, if you have to constantly calibrate the sensor anew.
When the thing that I showed at the very end is the case that all the sensors are rigidly attached to each other. We are working now on a case that, as you explained, they are not rigidly attached, but they are on an articulated body. When it's on articulated body, then you also need to solve what we call the forward kinematics between these two. So because we also measure all these angles. So there are some extra equations coming to the play.
Okay, thank you.
Okay, one more question.
Hi. A part of the use of point clouds for relocation and mapping, do you consider the use for, let's say, point cloud merging or the improving in different iterations?
I didn't quite get the question. So is it the question that using the point cloud to improve the resolution of it, or?
Yes, in different iterations, you can improve the resolution of the mappings or even merge different parts of the same scenario. Do you consider it as well in the
Yeah, when you do SLAM, basically now depends what you do. So basically, it's a probabilistic way of accumulating the hits of each laser points, some what we call voxels or bins, and that's of course accumulated. Now, that's one way of seeing it. So you have basically a three-dimensional environment where certain voxels have a number of hits that tells you that is a field full or not. That increases the resolution basically. Another way is to see it is that when you run a SLAM, basically you are accumulating spatially and in time all the points. When you move, you're basically also scanning. And if the scans are properly registered, meaning that they are in the same coordinate system, then basically increasing the resolution.
Thank you.